We'll move to the next speaker. So that is Dr. Zev Lovinger. He's a scientist at the Rafael Defense Labs in Israel. And he's going to talk to us today about measuring material strength and failure characteristics at high strain rates using EM-driven expanding cylinders. Over to you, Dr. Lovinger.
Yeah, so can you hear me?
Yeah, we can hear you very clearly. Yeah, thanks.
Okay, terrific. I'm just going to put this on a presentation mode. 1 minute. Okay, you see the slides? Hello? Hello?
Yes, we can see that. Yes.
Okay,
yes.
Perfect.
Yes.
Okay, so first of all, I'd like to thank the organizers for inviting me to give this talk in the symposium. I'm very happy for the opportunity. I'd like to send best wishes to Professor Simha on his retirement. I haven't worked with Professor Simha, but read quite a lot about his work since I knew I'm coming to this, participating in this symposium. And it was nice hearing the nice words by his colleagues yesterday. And if I could add something from my culture or language, I'll say, you probably know this, but Simha in Hebrew is joy and happiness. And from the stories about Professor Simha yesterday, it seems like this reflects a significant part of his personality. So I wish you much happiness in your next stage of life after your retirement. So getting to the presentation, this was a collaboration between Rafael, where I work. Next year it's going to be 20 years, and the Technion with Professor Ritel. And we are looking at measuring properties of materials at high strain rates. I will be giving, well, just a minute, something's not working here on the slides. Okay. Okay, sorry about that. Okay, so just a brief outline. I'm going to give some introduction about strength of materials at high strain rates, just for everybody to be on the same page. I'll show the experimental technique which we've developed, and show results for two materials we were working on. We started off with copper, and lately just got new results on tantalum, which I'll be showing, and eventually summarize and conclude. So in general, we're looking at behavior of materials at extreme conditions, and scenarios which are relevant to these cases. We're looking at impact, at explosive loadings, crashworthiness, and ballistics. And if we look even here on the right, we could see also some meteorites or hypervelocity if we're looking at fragments on space shuttles, etc. And in order to describe these cases, we're looking to characterize materials at these extreme conditions. And when I mean extreme conditions, we could more or less group them into categories, and which we'd like to test the materials and examine them for modeling and for describe these kind of scenarios. So we're looking at high strain rates, high temperatures, high pressures, and also shock loading, which, because of the instantaneous heavy side loading, has also significant properties when you describe the material behavior for such a loading. And in general, we would be looking to describe a function, a material behavior, with all of these under all of these regimes. And if we were in ideal life, we would like to examine each of these sensitivities for high strain rates or high temperatures, etc., separately. But as we'll see very soon, for many of these cases, especially when we're looking at extreme conditions, we're looking at a coupled regime, coupled effects of pressure and temperatures, for example, and we would like to try and overcome this to have a more proper description of the materials, and I'll be talking about this a bit later. So this talk will be focusing on high strain rate behavior. And when I'm talking about high strain rates, I'm looking at the range of 10 to the 3 to 10 to the 7. In general, if we look at impact loadings like per ballistics, or if we're looking at the interaction of material with explosives, we're talking about the regime of 10 to the 5, 10 to the 6. So this is part of that regime we're looking at. So the influence of strain rate on material strength is a complex issue. And if we could see here, this is a result from a paper by Follensby and Cox looking at copper. And we could see the strength of the material as a function of strain rate. And somewhere around 10 to the 3 to 10 to the 4 per second, we see a significant increase in the strain rate sensitivity. And this turn-up is an interest for many materials we're looking at, and especially how to get to this very high regime of strain rates. This threshold, or where we see the strong turn-up, is related to a change in dislocation mobility. And as we're looking at in the low regime at thermally activated dislocations, as we go higher, we're getting the effects of phonon drag, and the oscillations of the atoms are now interacting with the mobility of dislocations. So looking at this full regime of strain rates, there are, in the past few decades, several techniques for measuring strength. Of course, the split Hopkinson bar, we saw also a few works using the split Hopkinson bar yesterday. We could reach strain rates about 10 to the 3 to 10 to the 4. And then we have the Taylor test and the expanding ring setups. And on the bottom of the slide, we could see the higher rates with the different cases of plate impact tests and instability growth, which is reaching 10 to the 6 and 10 to the 7 per second. But one of the problems we have, especially when we want to reach the very high strain rates, is that we're getting these coupling effects, as I described it earlier. So just to summarize before we move further, so none of these experiments are actually a well-established technique, beside the Hopkinson, of course, which is very well studied and used. All of the other techniques, when we want to reach the higher regime above 10 to the 4, 10 to the 5, we don't have a well-established technique. And as I said, we're getting the coupling effects with the existing setups. One of the coupling problems which was dealt with in the past decade or maybe 15 years is the shock loading, which is causing significant thermal softening, sorry. And this can be overcome if you turn over to isentropic loading using wrap loading, for example, with magnetic forces. And just bringing here two examples of these nice machines, pulse current generator, the Velos, and of course the facility in Sandia. And just to point out how this generally works, we're looking at, if we see this illustration here on the bottom, we can have a small cartoon. We're putting a lot of energy in capacitors. We're charging it up to a few tens of kilovolts, and we have a fast discharge, which is discharging a very high current of a few megaamperes. And as this current is flowing through one conductor and coming through the other, we have repulsive magnetic forces between them, and they're pushing on the material, which we could then measure. So instead of impacting it or shocking it, we're just using very fast magnetic forces, but this ramp loading is not getting the heating which we're getting through shock. So having this in mind, when we were looking to examine the behavior of strength of materials, we were looking also to use a setup on the pulse current generator, and we're using the technique that we developed. We're using a pulse current generator using expanding cylinders. Using this technique, we could reach very high strain rates between 10 to the 4 to 10 to the 6. I'm going to explain this in the next couple of slides. And as we just started to establish this technique, we did a broad characterization on copper, which has it's a well-studied material and has a significant strain hardening effect. So we wanted to use that to see how this is working and comparing with the data in the literature. And just recently, we started to get new results on tantalum, which is also reported with a very strong strain rate effect. So we have this here on the bottom. You could see a paper we had out 2 years ago on this developed setup. So the cylindrical setup we're using instead of having the planar specimens, which I was showing before in that small cartoon, now we're looking at assembly of coaxial cylinders. The high current is flowing now through in the actual direction of the cylinders. It's going through one cylinder and coming back through the other. I'm going to show this cartoon just like before. So here's the current. It's coming down through the middle rod and then returning through one of the cylinders, and they're pushing now inwards, compressing the inner rod and expanding outwards the specimen. So what we're using here, we're actually using what's called a driver or a pusher configuration. Okay, the current is not flowing through the specimen itself. It's flowing through a cylinder, a conductive cylinder, which is pushing on the specimen itself. You could see the specimen here in yellow. And that has a very strong advantage because we're not heating up the specimen with the current which is flowing through it, and we could check we could use any material even if it's not conductive, like plastics and whatever. So this would be a very interesting setup to examine any material, and it doesn't have to be conductive. So this is just the pulse current generator we're using at Rafael. We have a capacitor bank system. We're charging up to about 30 kilovolts. We're getting 1 to 2 megaamperes, and the characteristic rise time is about 1 microsecond. And that's the most important number here, because that's the number that will characterize which strain rates we could reach. So theoretically, we're going to see that we could reach up to 10 to the 6 because of this very high rate. So here on the right, you could see one of the specimens as it's mounted on the pulse current generator. We have 4 PDVs. We're using interferometry to look at the velocity of the expanding cylinder under the dynamic loading. So we could design different specimens. We could characterize the magnetic field and then the magnetic pressure, and we could see characteristic sizes here. We have a inner diameter of 7 millimeters, and the wall thickness is between a millimeter and it's actually a quarter of a millimeter up to 2 millimeters. And we could vary the geometry and the voltage to adjust the magnetic pressures and reach higher strain rates. So how are we analyzing the strength from these materials? We're going to look at the velocimetry signals in a minute, but we're using numerical simulations and we're calibrating the strength to fit the velocity measurements we're getting in the experiments. We're going to look at the sensitivity of this in a couple of slides. So we started off with 2D and 3D hydrodynamic simulations just to examine the behavior of the entire setup. But eventually, to get the right accuracy when we're looking at the strength measurements, we came to realize we need to take into account the coupled behavior of the magnetic field and the hydrodynamic behavior of the cylinder. So the main tool we're using is 1D MHD hydrocode to analyze the behavior. So how does this look like if we look at such simulations? This is what's called, when you're looking at 1D simulations, we're looking at an RT plot, okay? The y-axis would be the radius, the x-axis would be the time. So each of the vertical lines here would be first would be the geometry of the specimen frozen at a specific time. And we could plot a 2D plot on all of this with different thermodynamic variables. Here we're looking at density. And if we go on, we could look at the velocity. For instance, we could see here at the beginning of the loading, we could see the reverberations of the waves between the cylinder. We could look at the temperatures. Of course, we want to see that we're not heating up the specimen above a specific temperature. And all of this could be characterized very well in this 1D analysis. Of course, we're looking at a strip in the middle of the cylinder, and it's not affected by the boundaries. So if we look at the velocity history, so what we could see here, the green thick line here is the experiment, and all the others are simulations with different strength. So first of all, we could see, if we look at the characteristic history, the current history, we could see that it's oscillating, and each of the steps we're getting here is referring to one of those oscillations. Okay, so that's how it's pushing it in steps. But if we look at the overall behavior, we can see that later on we're getting this kind of inclination of these of the velocity. So in fact, to explain this, when we're pushing with the magnetic forces the cylinder outwards, the only thing, of course, besides inertia, which is holding it back, is the strength of the cylinder, the hoop stresses. And we could see actually that, and I'll show you the two cases, like this, the pink one here on the top would be without any strength at all, and the green one would be with, let's say, 400 megapascals. And you could see that the inclination is strongly related to the strength of the material in the cylinder. And this is the main point we should point out. So looking at what I just said, if we're looking at this almost horizontal line, you would say, okay, so there's no strength to this in this kind of test we examined, but that's not right because, and this is the part I'm not getting into all the details, but we have around between 5 and 6 microseconds since the beginning of the expansion, we're getting failure of the cylinder. So in fact, this horizontal line is just looking at a fragment which detached, and we have no hoop stresses, so it looks like we're not getting any strength at all. So the important part of this technique is looking at the initial stage of acceleration, okay? And this is very important because we're looking at the forced stage of acceleration. Most of the analysis which is done on rings or cylinders are looking at the free flight stage, which is more here on the right. When you look at the forced stage, you can enjoy the benefit of the very fast rise time of the pulse current generator. And that's how we're reaching the very high strain rates in relation to other techniques which are looking at the expansion of rings or cylinders. So zooming in on this, again, we have those same slopes. It's just on a smaller period of time. Of course, this is not the way how we calibrate it. We do it in a more rigorous and mathematical way, just to visualize what we're looking at. So we could do simulations with different strengths and calibrate a material model or the strength which fits the inclination which we're getting here on these experiments. I'll show in a minute the results we got for copper, and I could say it was accurate up to about 50 megapascals. So we could get a very good accuracy from this kind of analysis. So these are the results we got for copper. We were examining the range of just over 2 to 10 to the 4. We were trying to reach 10 to the 5, but at the end of the series, we reached up to 7.5, 10 to the 4. And we were reaching up from around 310 megapascals to 450. If we compare that to the literature, so the results of this research are the blue dots over here. So we're comparing first to the results of Follansbee and Cox, and you could see first that the upturn is predicting something similar to what they were showing. They were showing just the onset of this upturn. And looking for additional results in the literature, we were looking at some pressure shear experiments that were done by Clifton and some students of Tong and Kuang. And comparing that, we saw that our results are predicting higher strength. Looking for reasons to explain this, again, we're looking at a coupled effect when we're looking at impact experiments. But I must say here that for these experiments, we're looking at the area of 5 GPa, so the shocks are not very high, and the expected thermal softening were below. But comparing the materials, the grain sizes were almost the same, but the material processing were different. We were using a rod, and they were using thin plates, and we believe this difference was the main one showing differences, and that is seen well in copper in the literature, showing differences in strength measurements, also in quasi-static regimes. Moving on to tantalum, and this is something we got in the past 2 weeks. So we did one measurement till now, but I thought it's interesting enough to show here in the symposium. So data in the literature is indicating high strength at extreme conditions for tantalum, and the responsible effects are still unresolved. if it's pressure, if it's behavior under shock. There are many papers and research done on this. And what's interesting first about our measurement here is that this measurement is a kind of standalone influence of strain rate hardening, okay? So this is a very strong advantage. We compared this in the literature, so there's work here on annealed and as received tantalum. We could see also differences here between the two materials, but they're more or less giving very close results. This is by Rittel and the group at Caltech. And additional results which were done in the isotropic compression experiments by Zev, Vogler, and others in Sandia. And in general, you could see that the result we got is bridging somewhere between the area of 10 to the 4 to 10 to the 6. This kind of cloud which I put here is because there's not a specific measurement of strength. That's part of the problems of these kind of measurements. Some of them are measurements which are done under release and some are under compression, and they're predicting different kind of strength. Going to the second
Dr.
stage of
Lovinger, sorry to interrupt, but you have 5 more minutes.
Yeah, that's fine. I'm going to finish in 3.
Yeah,
okay, so thank you. So examining the second stage, we're looking at failure mechanisms as we're looking at this fragmented cylinders which are soft catching. We could look at different failure mechanism. In general, we could look at tension and shear. Tension, we're looking at, of course, under the instability of necking and void initiation, and on the other hand, the evolution of shear bands. And one of the questions we wanted to examine is the failure mechanism dependent on strain rate, on the stress state? For instance, we could look at specimens evolving from 1D behavior from a ring over to a cylinder. And the methods we're using, first of all, we're looking at microscopy of the fragments, and currently we're developing an optic real-time diagnostics, which we would like to look at the diagnostics at the prior stage of fragmentation to try to examine how these failure mechanisms are evolving. Hopefully in a year or so, we will be able to present some results on that. So looking at the failure mechanism, so if we look at copper, so we look at the edges of these fragments. You could see here an example for the evolution of voids coming to a tension failure. We also have some arrested necks in these fragments, which become very interesting and nice to see. We could see the extensive plastic deformation here with a lot of twinning, evolution of voids. This is really just before the voids are breaking up the fragment. We could see also, on the other hand, some shear in some of these, a shear band evolved in some of these fragments. And again, we're going to do some extensive characterization, looking also at some statistics of these results. We did the same for tantalum. They're not as interesting. We see again all these extensive plastic deformation of twinning, etc. But one interesting thing is, as we look at the edges of these fragments, we could see this kind of pinching, which is very characteristic when you look at quasi-static testing of tantalum and even with Hopkinson experiments. But we were expecting, as we got to very high strain rates, to see something a bit more brittle, but it's surprisingly very nice how we're looking at these kind of pinching behavior, just as we see at the lower regime. And we're expecting, looking forward for the newer experiments we're going to see in the next few weeks and months. So just to summarize, I showed you here the new experimental setup and methodology to look at strength at very high strain rates. The advantages of this technique, again, it's shockless, so we're looking at low pressures, there's no temperature softening, and this is allowing a standalone influence of strain rate hardening, and that makes it very kind of desirable. We use a pusher so we can measure all materials. It doesn't have to be conductive, and we're looking at the 4-stage acceleration, and that's how we're taking advantage of the very fast behavior of the pulse current generator. If you have a faster pulse current generator, you could get even to higher strain rates. So we looked at copper and tantalum, and as I was showing at the last slides, we're looking at the microstructure to explore failure mechanisms, and currently developing some more advanced diagnostics to look at these characteristics. That will be all. Thank you very much.
Okay, thank you, Dr. Lovinger, for a very nice and interesting talk. We have one question from the attendee, so I'll just read it out.
Okay.
So he has said that I'm just curious about how big the complete experimental setup is.
Okay, so the pulse current generator, it's a machine the order of 2.5 meters by 2.5 meters. And the specimen itself, I showed the dimensions. Okay, it's just a very big setup because you need these quite a few capacitors and to achieve these kind of currents.
Okay, yeah, thank you. Mr. Vijay Chalivendra, you can directly ask your question about the velocity measurement. Hello, Mr. Vijay?
Yep.
Yes, please. Thank you. How did you measure the yield strength value from the velocity measurements, please? I might have missed the slide.
Okay, sure. So the yield strength, we're looking at as we're looking at the profile, we could see that these inclinations in the velocity profiles are correlated very strongly to strength. And we did a very strong, like a broad sensitivity examination of this, and you could get a very good sensitivity. As I said, for copper, we got a sensitivity of just about 50 megapascals, looking at analyzing this for different types of strength. Again, we're looking just at an equivalent plastic strain, like an EPP model, an elastically perfectly plastic behavior. The information here can't give like a hardening mechanism, etc., but it would give the overall strength we're seeing at this stage of acceleration of the cylinder.
Okay, thank you.
Okay.
Mr. Advait, yeah, you had a question, you can directly ask the question. Mr. Advait? Hello? Mr. Advait?
Looks like his hand is raised.
Your hand is raised. No? Advait, Mr. Advait, your hand is raised. Can you just directly ask the question?
Sorry, sir. Actually, it get placed. Sorry, sir.
Okay. So you don't want to ask a question?
No. Sorry, sir.
Okay. No problem. Okay. So then, Mr. Saurabh, can you ask your question? Hello, Mr. Saurabh, can you just ask your question?
Can you unmute? Saurabh?
Can you unmute?
Hello?
Yeah.
Sir.
Go
Sir,
ahead.
how the grain size is correlate with the high strain rates is my question. Means how we can correlate our grain size with the strain rate.
Oh, wait. So if you could just elaborate on that a bit. I mean, we characterize the initial microstructure, like the grain size, like you could see here for tantalum, for instance.
Right.
We don't see any changes in the size or refinement of it. And we're just looking at, more or less, you could see here at the order of 5 to 6 grains across the thickness. This is only 250 micrometers, like a quarter of a millimeter. So we're getting about 5 to 6 grains, but we didn't see any evolution of strain rate under these experiments. Of the grain size, I mean.
Okay, sir.
Okay, I think we'll go to the last question. So, Dr. Narayan Sundaram, you can directly ask your question.
Hello, Dr. Lovinger, and nice talk. I just had a couple of quick questions. One is, you mentioned being able to uncouple all these effects, but what about the effect of the Taylor-Quinney heating at these strain rates? That was one question. And the other question is, can you increase the strains you get to? I mean, your strain rates are reasonably high, but you showed a strain of 0.15 in one of the figures. So can you get to a larger number? Those are my two questions.
Okay, so the heating, of course, under strains, like the energy of the plastic strains will be there anyhow, of course. I think when you calculate the overall temperature rise from that, it doesn't have a significant effect for most materials, I'll say. Maybe not for all of them, but for most materials, this kind of heating reaching tens of up to about 100% of strain wouldn't be very significant. We are reaching here high strains. We are reaching here failure strain of about 70%. I'm just comparing what you showed there at what you saw at 0.15 was just a strain which is compared to other data in the literature. These graphs of strain rate sensitivity is usually referred to a specific plastic strain. So that's why I mentioned 0.15, but I would say that this measurement I made would be valid up to about 0.5 in this measurement.
Okay, yeah, thanks. That answers my question.
Sure.
Okay, so let us thank Dr. Lovinger for a very, very nice and interesting talk.
Thank you very much.
Thank you, Dr. Lovinger. Yeah, yeah.